Alright, then let's get started. Just a second. This is getting recorded. Hello everyone, I am Sashi Siddharth. I am a, I am a PhD student associated with the Center for Systems and Control at IIT Bombay, and I'm also the TA for this course, Senior Dynamical System. So welcome to second week's lecture. So let's get started. Just one second. I'll discuss the following topics. This would be the concepts of geometric multiplicity, geometric multiplicity of eigenvalues, use these concepts to find out how to compute Jordan blocks, and then finally how to compute power of a matrix, for example, e to the power 100, or let's say the state transition matrix for LTI systems, e to the power 80. Then we'll talk about uh, stability analysis, output stability, and its relation with stability for LTI systems. Alright, so let's get started. Let's start with a question, and I'll describe these quantities as we progress along the question. Alright, so we have a matrix, a second order system. So it is a matrix 0, -2, 1, 3. And we have to compute power 100 and e to the power 8. Alright, so to compute these matrices, we need the concept of Jordan block. So Jordan normal form of a matrix A. So A and B is squared matrix of size n by n. Note the Jordan normal form by J. So J is given as PA plus. So we'll find out what this matrix P is to form the matrix J. But the matrix J is going to be of this form. So J1, J2 up to, let's say JL, and then zeros here. So these J's can be matrices of smaller dimension, or they can be constants as well. So they can be constants, real numbers, or some matrix of size, let's say a smaller dimension, maybe n1 by n1. But we have a diagonal structure here. So the off diagonal elements would always be same. Okay. It's for it's just a Jordan yeah, it's just a Jordan normal form of a matrix. We're not talking about LTI or LTV systems as of. But the question is for an LTI system because we have a constant matrix A. So mhm. Alright, so each of these JIs are blocks. So I would say JI is a Jordan block. It corresponds to an eigenvalue. So for example, for some eigenvalue lambda I of a matrix A, the Jordan block is like this. So this is going to be a smaller dimension than n. Let's say something 1 by 1. And this is lambda I, lambda I, lambda I on the diagonals. And then 1 above any one. So 1, 1 and so on. 0 is here also. So one of the main points is the dimension of this matrix N1. So this is known as the algebraic multiplicity. So of lambda I. So let's see. So for example, if there was a matrix A which had an eigenvalue 0, but which had an algebraic multiplicity of 2. So the Jordan block corresponding to this matrix, the corresponding to this eigenvalue would be 0, 0 on the diagonals, which has to be a 2 by 2 matrix, and 1 above the main diagonal. This is the Jordan block corresponding to lambda equals 0 when algebraic multiplicity is 2. Alright. We'll look at what is geometric multiplicity, but let's first concentrate on this. So to get the Jordan normal form, we need the matrix P. So to form the matrix P, the first step is to compute eigenvalues and eigenvectors. Values and sorry, eigenvectors of the matrix P. Alright, so then step 2 is, so for example, you have some eigenvalue lambda I. If the I algebraic multiplicity is 1, that just repeats once, so the Jordan block would just be a constant, which is exactly lambda I. Then if for lambda I, you have algebraic multiplicity 2, then the Jordan block would look something like this. And then so on for higher order of algebraic multiplicity. Okay. So right now we have a matrix. So A is 0, -2, 1 and 3. So the eigenvalues are going to be the roots of the characteristic equation. That is determinant of lambda I minus A. That should be equal to Z. So let's see. Lambda and then 2 minus 1 and lambda minus 3. The determinant should be 0. Minus 3 plus 2 equals 0, which is lambda square minus 3 lambda plus 2 equals 0. So the roots are, so let's see. So one of the roots are 1 plus 2. So you can see that they are not repeating. So algebraic multiplicity is 1 and algebraic multiplicity is 1. So the Jordan block corresponding to this is going to be 1 and this is 2. Alright, now let's look at the eigenvectors. So corresponding to this one. That is going to be, so let's see, we have the matrix 0, minus 2, 1, 3. This is the eigenvector equation, eigenvector eigenvalue equation. We're saying that we have some eigenvector v1, v2 equals to lambda times. We have to solve for v1 and v2. So let's see. So minus 2v1 equals v1. This is, sorry. This 2v2 equals v1, which is v1 plus 2v2 equals 0. And the next one is v1 plus 3v2 equals v2. This implies v1 plus 2v2 equals 0. So let's assume that v1 is 1. This implies this half. Right. Or what you can do is assume v2 to be 1. Have an eigenvector minus 2, 1 is non-unique. Alright, similarly, eigenvector corresponding to lambda equals 2. So eigenvector corresponding to lambda equals 2. So here we have the equation 0 minus 2, 1, 3 v1 v2 equals 2 times v1 and v2. So let's see what the equation is. Minus 2 v2 equals, which is v1 plus v2 equals 0. Now the next one is v1 plus 3v2 equals 2v1, which implies again v1 plus v2 equals 0. Right, so what we can do is assume v1, which implies v2 is minus 1. So one choice of eigenvector for lambda equals 2 is this. Alright. So the model matrix, I'm going to make this as model matrix P is given as, so I'm going to arrange this, the columns of P are actually the eigenvectors for the corresponding eigenvalues. So this is for lambda equals 2. So this is minus 2, 1, 1 and minus 1. And we also need P inverse to find out the Jordan normal form. So this is a simple second order, second dimension matrix. So this is 1 upon determinant of P. So this is just one. Then we'll swap this two and we have. Alright, so the Jordan normal form is PAP inverse. Yeah, minus 2, 1, 1 minus 1. Then we have A, so it is 0, minus 2, 1 and 3. B inverse is minus 1, minus 1, minus 1, minus 2. Yeah, just check this one. This is P inverse AP, which is 2, 0, 0, 1. Alright, so observe that if lambda is algebraic multiplicity 1, then G is matrix containing lambda i's on the diagram. So now we'll use this Jordan normal form to compute e to the power 80 and e to the power 100. Alright, so we have J equals P inverse AP, G implies we have P J P inverse equals A. Okay, so then e to the power 100 is nothing but P J to the power 100 P inverse. And this special thing about J to the power 100 is it's just the 100 power of the diagonal elements because J was a diagonal matrix. So this is easier now. So we have 1 minus 2 minus 1 1, 2 to the power 100 0 1, and then so this is the answer. I'm going to write the final answer directly. You can check this later. This is 2 minus 2 to the power 100 1, 2 to the power 100 minus 1. Similarly, we need the exponential of the matrix A. So we have e to the power 80 is now P e to the power jt P inverse. So again, because we have that special diagonal form, the Jordan normal form, this is simply e to the power 2 times g e to the power t. So exponential of the elements on the main diagonal of J. And then P inverse. So this is minus 1, minus 1. So I'll write down the answer directly. This is 2 to the power t minus e to the power 2t. Power 2t minus e to the power t. So we can observe that if this was a straight transition matrix of some system characterized by the matrix A, system would be unstable. Why? Because all the exponential have positive parts of t. So if you have some initial condition, let's say x naught is for a second order system, let's say it's 1, 0, and we have this LTI system, then the solution is going to be e to the power 80 times x naught. And with this initial condition, we just have the first column. So to e to the power t, part 2t, e to the power 2t minus e to the power t. And this is just growing as time increases. So therefore, the system is not stable. Alright, so I hope that this question was clear to you. Now let's move on to the next topic, stability in the sense of life. We've already seen some of the concepts in this question, so let's begin with question 2. First of all, we have compute e to the power 80 for a equals 0, 1, 0, 0, 0, 0, 0, 0, 1, minus 2. We have to comment on the stability of the system. So system x dot t equals a x of t asymptotically stable. Stability in the sense of level. So we have just seen in the previous question how to compute e to the power 80. But observe that this is a very large matrix. Its dimension is 3 by 3. So we'll have to compute eigenvalues and eigenvectors and then form the model matrix and take its inverse. So what we can do is, instead of that, so let's see if this matrix A has some special form. Okay. So you can observe that we have minus 2 here and a Jordan block for 0 here. Right? So let's just check first if the eigenvalues are 0 with algebraic multiplicity 2 and the other eigenvalue is minus 2. So that's easy. We just have determinant A minus lambda I equals 0. So let's see. Lambda minus lambda minus 2 minus lambda and 0, 0, 0. It should be 0. Okay, so we have minus lambda, again minus lambda minus 2 minus lambda equals 0. So this is the second order algebraic multiplicity, lambda equals minus 2, algebraic multiplicity 5. So you can see that the matrix A is already in the Jordan normal form. Now let's compute e to the power 8. Alright. So now we look at how to compute the exponential when we have some repeating eigenvalues. For example, e to the power 80 for a diagonal element is simply e to the power minus 2t. But we'll now see how to compute the exponential for a Jordan block of size 2. Alright. So this would be again a third order, so 3 by 3 square matrix. Zeros here, e to the power minus 2t, and this is going to be 1, 1, and t. You can also check this, but this is e to the power 80 for this Jordan block. So what I have written is e to the power 0t, t into e to the power 0t, like this, and 0t. So if I had some other eigenvalue which had a Jordan block of size 2, then it would be for some lambda I with Jordan block of size 2 by 2, e to the power jit would look like e to the power lambda it, t into e to the power lambda it, 0, and e to the power lambda it. Okay, so we have e to the power 80, and we have to comment whether the system f dot equals a x of t is asymptotically stable. Okay. So let's say we have some initial condition, say x naught is 1, 0, 0. So the solution is going to be e to the power 80 times 1, 0. It's just the first column. So we have a constant vector. So from the initial condition, we're still at the initial condition. Alright. So this means that x of t does not converge to 0 as t tends to infinity, right? Because it just remains 1, 0, 0. So this implies that the system is stable. Okay. Now we have to comment on whether the system is stable or not in the sense of Lyapunov. So let's see. So I'll write down the definition. So actually you can refer to, I think, slide 18, which talks about stability in the sense of Lyapunov. So if the eigenvalues all have negative real parts, then the system is of course asymptotically or exponentially stable if it's an LTI system. And if we have some eigenvalues which are on the imaginary axis or have positive real parts, then they should have Jordan block of size 1. But you can see that lambda equals 0 have a Jordan block of size 2 by 2. Therefore, the system is not marginally stable or the system is unstable in the sense of lambda. So if this is clear, let's move on to the next question. This question focuses on stability of an LTV system and how do we form internals. So we'll talk about linearization of the LTV system. So on solutions to the following nonlinear system. First to the origin. So what we are trying to find out if the nonlinear system is asymptotically stable or not. Mention in R2. So we have a state space of second order. Start sufficiently close to it. So this gives us a hint to linearize the system. Linearize the system about the origin. So I'm going to write down the system. So x1 dot and x2 dot. This is minus x1 plus x1 and square. So we can see that it's a nonlinear system plus x2 square and then minus x2 and then we have a sine function. So again nonlinear. We want to convert this to a system like this, where the matrix A is actually the Jacobian, right? So let's say this can be written as f1 of t, f2 of t. So we can write this as these are actually functions of the states. So let's say x1, x2. This becomes del f1 by del x1, del f1 by del x2, again del f2 by del x1, and del f2 by del x2. So I'm going to write this down directly. You can check. This one. So I have x1 squared, and then this is just 2x1 is 2. Then this is minus cos x1, then minus 1. Okay, and we have to compute this at the origin. This one 0, and minus 1 and minus 1. Okay, so we'll talk about diagonal of these things. So denominator b minus lambda equals 0. And minus 1 minus lambda, this should be 0. Now repeated eigenvalues with negative real parts. So in the sense of diagonal, the system is asymptotically stable. So with the nonlinear system, locally asymptotically stable. So this is how we comment on the stability of a nonlinear system. So we linearize it about the origin or about the equilibrium state and form the A matrix and then comment on the eigenvalues. Alright, so let's see. So now we'll talk about another way to comment on stability of LTI system. So this is let me check question. Alright, system. So it goes -1 to 0 -1 x. So we have an LTI system and we have two partial expression. First we have the P matrix equal identity. To the diagonal equation A transpose P plus PA and then comment on whether we can include any of them. Stability of the system. Next part is now we have been given Q instead of P. So compare P with Q equals identity. And again the question is the same. Now can you conclude? Stability of the system. Okay. So before we start this question, let's recall the concept of the Lyapunov equation and how it's useful in determining the stability of LTI systems. For that, for every skill, we can find again a symmetric positive definite P, which solves the Lyapunov equation. Which is A transpose P plus PA equals Q. So if just note that if the system is asymptotically stable, so if the system again LTI system asymptotically stable, then P is positive definite. So the symmetric matrix is positive definite. Let's see. PQ. We have to do is given Q, we can find P, which solves this equation, and then find out if P is positive definite. So if P is positive definite and symmetric, then the LTI system is asymptotically stable. But observe that the first part already talks about a given P, and then we have to conclude about the stability of the system. Alright, so let's move on. P is high, and the matrix equation is A transpose B plus BA, which is A transpose plus A. Okay, so we have minus 1, 2, 0, minus 1, 2, 0, minus 1. This is minus 2, 2, 2, minus 2. Okay. It is actually on the negative signs and we will have this minus 2. Let's say this is minus 2. It becomes 2 minus 2 minus 2, 2. So Q is symmetric. So here's Q transpose is 2 minus 2 minus 2, 2. Now let's see if Q is positive definite. So to see that, we have to compute the eigenvalues of the matrix Q. So we have determinant Q minus lambda I equals 0, which is it should be 0. We have 2 minus lambda square minus 4. 4 plus lambda square 1 minus 4 lambda 0, 0 and 4. So okay, so Q is positive definite. Correct? The eigenvalues of A to comment on the stability of the system. So let me just write down what A is. Minus 1, 2, 0, 1, minus 1. So our determinant A minus lambda I equals 0. Minus 1 minus lambda 2, 0. Z. So this is minus 1 minus lambda square 0. So Q is now positive definite because one of the eigenvalues is exactly 0. Right. Yes. Not positive definite. Okay. So the conclusion which we get from here is given Q and given P cannot conclude stability of the system. Because we just saw that even though the Q which you obtained was not positive definite, we have a system with negative eigenvalues. So we have a stable system. Alright. So we also have the second part of this question, which is straightforward. So we have been given Q as identity. Now we have to find P and then comment on the stability of the system. Okay. So the Lyapunov equation is A transpose P plus PA equals minus Q. Say that at the outset, assume that P is symmetric. So this is a second order system. We have a 2 by 2 matrix which is symmetric. So we have P1, P2. So this is also going to be P2. And let's say this is P4. It's P2. Okay, so this already implies that P is P transpose. Okay. So now let's substitute this matrix. So P is minus 1 and the transpose to 0 and minus 1. Then P1, P2, P2 and P4. P times A minus 1 to 0 minus 1 equals minus identity. So this will lead to two linear equations in P1 and P2. So let's see, and P4 actually. So we have minus 2P1, 2P1 minus 2P2, 2P1 minus 2P2. So it's minus 1, 0, 0, minus 1. So we have four equations and three unknowns. Alright, so let's see. So equation 1 is simply minus 2P1 is minus 1, which implies P1 is half. Then we have 2P1 minus 2P2 equals 0, which is half. And then 4P2 minus 2P4 equals minus 1. Get 3 by 2. Alright, so the P matrix is P1, P2, and P4. So now we have to find out if this is positive definite or not. So we'll just compute the eigenvalues. So P minus lambda equals 0. This implies I have half minus lambda, 3 by 2 minus lambda, half and half. It should be 0. Okay, so let's see. square minus lambda. Check if this is correct. So this is 3 by 4 minus half lambda minus 3 lambda by 2 plus lambda square minus 1 by 4 equals 0. So we can multiply by 4 throughout. So we have 3 minus 3 lambda plus lambda plus 4 lambda square minus 1 equals 0. Alright. Square is into lambda plus 2 equals 0. Three lambda square minus 4 lambda plus 1 equals 0. So you can calculate the roots of this equation. I'm going to write this down directly. So these are real roots. So 1 plus 1 by root 2, 1 minus 1 by root 2. Okay. So this one is positive, and this one is negative. Let me just, this is also positive. So we have positive eigenvalues of a symmetric matrix P. So this implies that E is positive definite, which implies that a system is asymptotically stable. So this question was clear to you. Let's move on to the next one. This is the fifth question. So again, we have a system. So described by x dot equals minus 1 1 minus 2 3 still asymptotic stability popular equation and Q equals R. So again, let's assume that we have some matrix P which is symmetric. So P is P1, P2, P2, and let's say P2. And now we'll just plug it in the Lyapunov equation. So we have A transpose P plus PA equals minus Q. So we have minus 1 1 minus 2 3 1 P2 A equals minus identity. So now again we have equation. So minus 2p1 minus p2. And this one is minus p2 plus 6p4. This is minus identity. Alright, so let's see. So we have two equations which is with the same answer. So p4 is 0 and minus 2p1 plus 2p2 minus 2p4 equals 0. This one implies minus p1 plus p2 minus p4 equals 0. You can solve the system of equations. So I'm going to write this one as equation 1, 2, and we have two equations. So 2 plus 6p4 equals minus 1. Right. So the solution of 4 is p1 is 0, p2 is 1, and p4 is 0. So you can also check these by substituting in all the four equations. So the matrix P is given by 0, 1, 1, 0. Okay, so now we have to talk about the eigenvalues. So again, P minus lambda by this determinant is 0. Lambda square minus 1 is 0, which is sorry, it's not imaginary. Alright. So you can see that one of the eigenvalues is negative. So P is not positive definitely. Which implies that the LTI system is unstable. So let's verify if it is indeed unstable or not. What we can do is find the eigenvalues of the matrix A. So I'm just going to write down the eigenvalues directly. You can check these later. The eigenvalues of A are this as positive K part, which implies that the system is unstable. Now we'll talk about Vivo stability. So let's consider the question. So she called that for Vivo stability. So the system is continuous time system is uniformly Vivo stable. in statement. So if an only three pole or the entry of the transfer function, the transfer function has a strictly negative real part. The transfer function is C SI minus A inverse B plus D. We saw this in the last week's tutorial session too. Important note that for LTI systems, as B was taken. Let's look at a question. The LTI system equals xt, so we just have one stage, it's a scalar system, and the output is 0.5 xt is 0.5 So Vivo stability talks about output, so the output is also mentioned here. Now let's see. Okay. So x dot equals x implies that A is just regular number 1, B is 0. Y equals 0.5x plus 0.5u implies that C is 0.5, D is 0.5 as well. So the system, this is an LTI system is Vivo stable if and only if the transfer function is negative real poles. So the transfer function G hat of S is C S I. So I is just a scalar 1 and this one inverse B plus D. Just 1.5. It does not have any poles. Transfer function has no poles and therefore condition to satisfy. So the condition that poles of G hat S system is LTI system is Vivo stable. So let's hear about the Lyapunov stability of the system. So A is 1. So we can see that the eigenvalue is positive. So however, since it's strictly greater than 0, therefore we conclude this system is not stable in the sense of platinum. So we have a very important property, stability does not imply lack of stability of an entire system. So I hope that this question is clear to you. Now let's move on to the next one. Transfer function of a given entire system. T is minus 2 1 0 0 0 0 0 0 minus 1. 1 0 minus 1 and C is 1 1 1. It's a system B was stable. So we just have to compute the transfer function and comment on the stability. So B is 1 here. Transfer function is G hat of S equals C S n minus A inverse B plus D. Just going to write down what Sn minus A inverse is. So B hat of S is 1 by 1 plus 2 Sn is plus 1 and we have 1 0 minus 1 plus 2. So let's see how to compute the inverse of this 3 by 3 matrix. So let's say that we have Z1, Z2, Z3, which is going to be equal to S plus 2. Let's say with 3 is US. So we know that this is going to be a 3 by 1 vector because G hat S is a scalar. So we are going to denote that 3 by 1 vector as Z1, Z2, and Z3. Now we have to find out what Z1, Z2, and Z3 are. So we can multiply by inverse and we have x plus 2 minus 1 0. 0 is 0, 0 is plus 1. Is 1 0 minus 1. Okay, let's see. So you can see that this is an upper triangle form. So this is, yeah, take 3 simply minus 1 over x plus 1. Then we have 1 upon s plus 2. So observe that we didn't really compute the inverse of the matrix. So now we have the transfer function g hat of s equals 1, 1, 1, and 1 over s plus 2, 0, minus 1 over s plus 1, plus 1. So this is the denominator is, so k s plus 1 minus 1 s plus 2. I have to comment on the poles of the transfer function. So the poles of the system of transfer function are x equals minus 1 minus 2. System. So these are strictly negative. Therefore, the system is stable. Solve the strictly negative real parts. Next question. So consider the following system. T is 0. Is to 0, 0, 0, 0, 1, and 0, 0. B is the column vector 1, 1, 0, and C is 1, 1, 1 as in the previous question. Okay, so we have three parts to this question. First is transfer function. The matrix A asymptotically generally stable or unstable. As part is the system B was stable. So let's compute part B first because it doesn't require the transfer function matrix. So let's see. The matrix A is is to 0 is 0. Sure, just 1 second. Okay. 0 0 1 and 0 0 0. So you can compute that the eigenvalues are again 0 0 and -2. And observe that this matrix A is already in the Jordan normal form. The Jordan block of 0 here is 2. So we have a Jordan normal block. It's a Jordan block of lambda equals 0 is of size 2. So you can see that the algebraic multiplicity is 2 here. So therefore, the system is unstable. If we had a Jordan block for lambda equals 0 as just a scalar, then the system would have been marginally stable. The system is unstable in this case in the sense of Laplace. Right now, so to comment on whether the system is Bibo stable or not, we first have to compute the transfer function. So let's come back to part A. So just observe that D is 0, G hat S is simply C Si minus A inverse B. This is 1 1 1 and then S plus 2 S S minus 1 inverse times let's see what B is 1 1 0. So again, we don't have to compute the inverse of the matrix. Say this is a 3 by 1 vector denoted by Z1, Z2, Z3. Two 0 0. 0 is minus 1, 0 0 is two 0 0. Z3 is it. Alright, so again we have a nice upper triangular form. Z3 equals 0. SZ2 equals 1. So Z2 is 1 over S. 1 over S plus 2. Right, so G hat of S becomes C times Z1, Z2, Z3. So 1 over S plus 2, 1 over S and 0. This is 1 over S plus 2 plus 1 over S. So the poles are 0 and -2. So this is not strictly negative. So Just go to part B, that the system is stable. Since there is a rule, so the system is unstable in the sense of lateral, and the system is also not pivot stable. So the next question. So this focuses on computing the minimal polynomial matrix. So compute the characteristic. Equals 1, 3 minus 2, 0, 4 minus 2, 0, 3 and minus 1. This polynomial is simple to compute. It is simply the determinant of a minus lambda I. Zero. So this implies we have 1 minus lambda, 4 minus lambda minus 1 minus lambda, 3 minus 2, 0, minus 2, 0, 3. Should be equal to 0. So this implies 1 minus lambda. So let's simplify this. Lambda square minus 5 lambda plus 2 equals 0. Just check this. So this is plus lambda. So this becomes minus 3 lambda. So one of the roots is 1. So lambda plus 1. And the other one is 2. Let's see. We have minus 2 equals 0. So we don't have to compute the eigenvalues values. We just have to expand this to get the characteristic polynomial. So the characteristic polynomial is this one squared, lambda minus 2 equals 0. So look at this is the characteristic polynomial. So since this is the characteristic polynomial, we can also expand this and get the expression. But let's keep this in this format. So according to the Cayley-Hamilton theorem, so we can substitute A instead of lambda. So A minus identity, A minus 2i into C. So now let's consider another polynomial. So we are going to name that polynomial m lambda. So m lambda is lambda minus 1 and lambda minus 2. So we are not considering lambda equals 1 twice. So if we substitute A, we have A minus I is 2. So MA is, we have A square minus 3A minus A. So that so you can substitute A here and verify. So this is 0. So observe that the value of the minimal polynomial that equals A is 0, even though MA is not the characteristic polynomial. So also observe that degree of m lambda is lesser than the degree of the characteristic polynomial. So this means that therefore we can conclude lambda the minimal polynomial of A. Alright. So we did 9 questions today. That's it for this week's tutorial. So let's revise. We'll go to the top again. So we discussed 3 topics today. One was to compute the Jordan block, the Jordan normal form, the eigenvalues, the eigenvectors, and exponential and powers of A using Jordan form. Then we talked about Lagrange stability, and then finally we talked about Weber stability and its relation with Lagrange stability for LTI systems. So in first question we saw how to compute e to the power 100 and e to the power 80. So we first computed the J matrix using the eigenvalues and eigenvectors. So how to compute the Jordan block for any lambda of algebraic multiplicity n1. Okay. From the model matrix P, found out J by P inverse AP, and then found out e to the power 100 and e to the power 80. Right. After that, we looked at how to comment on asymptotic stability of the system by looking at the eigenvalues of A. So the stability of the nonlinear system. So we linearized the system about the origin and then commented on the stability of the nonlinear system using the A matrix, which is the Jacobian of the system. Alright. Next couple of questions dealt with Lyapunov stability analysis using the matrices Q and P, which are related to the solution of the Lyapunov equation. And this was these are questions 4 and 5. And then we talked about Vigo stability and how it's related to the transfer function of an LTI system. We also looked at the fact that Vigo stability does not imply Lyapunov stability of an LTI system. Green is happy. And then finally, we talked about the minimal polynomial of the matrix A, which we found out for a 3 by 3 matrix in the last question. Alright, so that's it for today. Thank you.